Welcome back, everyone. In this video, we're going to learn about redox chemistry. We've already talked about it a little bit in the context of it being a driving force for chemical reactions, and now we're going to go into a little bit more depth about that. So as we mentioned already, we've talked about 4 different driving forces for chemical reactions. We have formation of precipitate, formation of a weaker non-electrolyte, or formation of a gas. And in this video, we're going to go in depth about the 4th type of driving force, which is redox chemistry. So redox reactions involve a transfer of electrons from one reactant to the other reactant. We have some terms that we need to be familiar with. One is oxidation. Oxidation is defined as the loss of electrons. We also have reduction, which is defined as the gain of electrons. Hence, the name redox is a combination of reduction and oxidation. An oxidizing agent is a substance, whether it's a given element or a molecule, that causes the oxidation. Because the redox process involves a transfer of electrons, there always must be one substance that gains electrons and one substance that loses electrons. Therefore, the oxidizing agent is itself being reduced, and the reducing agent, which causes the reduction of the other substance, is itself oxidized. So if you can identify the oxidizing agent, then you know what the reducing agent was if there's only one other substance. We can visualize this using this diagram here. What we see is that substance A has 2 electrons in excess, and it gives them to substance B. Because substance A is losing electrons, that's oxidation. It's being oxidized. And because substance B is gaining those electrons, then we say that it has been reduced. Therefore, A reduced B and B oxidized A. There are a couple mnemonics that can help you to remember the definitions of oxidation and reduction. One is oil rig. This is short for oxidation is loss, referring to loss of electrons, and reduction is gain, referring to gain of electrons. So oil rig means oxidation is loss of electrons, and reduction is gain of electrons. Another mnemonic is Leo goes Gur, as in Leo the lion. Leo the lion goes Gur. This would stand for to lose electrons is oxidation, to gain electrons is reduction. So you'll notice that these 2 mnemonics are really just saying the same thing. You can pick one or both of them to use, or you can come up with your own. As we've seen already, single displacement reactions are redox reactions. So if we take a look at the reaction between zinc metal and aqueous copper sulfate, we might have a copper sulfate solution and you put a piece of solid zinc metal in that solution. What happens is the zinc metal gives up its electrons to the copper ions, which causes the copper ions to solidify, and the zinc dissolves into the solution. So our balanced chemical equation is what you see here on the screen. If we wanted to write out the full or complete ionic equation, remember, we will dissociate any strong electrolytes. So copper sulfate is an ionic compound that's aqueous, therefore it gets fully dissociated. Zinc sulfate is also it's aqueous, so it could be a strong electrolyte, and because it is an ionic compound, it is a strong electrolyte. It's a salt, so it fully dissociates, and then we're left with the solid copper. To write out the net ionic equation, we cross out the sulfate ion, and we're left with zinc metal reacts with copper ions to produce zinc ions and copper metal. And so essentially what we've done here is we see that the zinc metal, again, has gone from a neutral charge to a positive charge, so it has lost electrons. Copper has gone from a positive charge to a neutral charge. It has gained electrons. And so we can write out the processes for each of these 2 substances, both for zinc metal and for copper ions, independently. And we can do so in what we call half reactions. So if we identify the substance being oxidized, remember oxidation is the loss of electrons. Zinc is the element losing its electrons. And so we express that as zinc metal going to the zinc ion, and the product also contains 2 electrons. And we show that those are dissociated from the zinc metal. To identify the substance being reduced or the oxidizing agent, we ask what substance is gaining electrons. Again, we see that copper went from a positive 2 charge to a neutral charge, therefore it must have gained 2 electrons. And what we see here then is that the number of electrons being gained by copper is equal to the number of electrons being lost by the zinc. And that's what we should see for any redox reaction, that in order to, when we combine these 2 half reactions, they get us our net ionic equation, and the electrons disappear, at least in the net ionic equation. So as you saw in that previous example, I talked about the charge of the species and how we are able to use that to identify whether a substance was gaining or losing electrons. This brings up the notion of what we call oxidation state or oxidation numbers. And these are used to track the electron flow. In the ebook, at the stop sign, it walks you through the rules for determining oxidation numbers. And you need to be able to apply these rules to determine the oxidation number or oxidation state for any substance, and then use that information to identify whether or not a redox reaction is occurring. So the first rule is that for any atom that it's in its elemental form, the oxidation state is 0. For example, chlorine or oxygen, phosphorus, copper, sulfur, these all have an oxidation state of 0. For monoatomic ions, the oxidation number or oxidation state is equal to its charge. So for chloride, its oxidation state is -1. For iron 3+, its oxidation state is +3, etc. Then, when you have elements that are in molecules, they will have common oxidation numbers that can be used as a reference point for determining the oxidation numbers of other elements in that same compound. So group 1A metals always have an oxidation number of +1 when they're as an ion. Group 2 metals always have an oxidation number of +2 when they're in a compound. Hydrogen will generally be +1 unless it's bound as a hydride to one of the group 1 or group 2 metals. So sodium with hydrogen, sodium will take a +1 and hydrogen will take a -1. Fluorine, it will always be a -1 when it's in a compound with other elements. Oxygen is almost always going to be -2. The exceptions to that include peroxides or superoxides. And then your halogens, the other halogens, chlorine, bromine, and iodine, those are typically -1. And we'll see some exceptions to that. So if you have a molecule or an ion, then the sum of the oxidation numbers of each element within the molecule must be equal to the overall charge on the ion. So for example, if you have hydroxide, then the sum of the oxidation numbers must add up to be -1 because the charge on hydroxide is -1. That would mean we'd have hydrogen that has a +1, oxygen with a -2, and so the sum is -1. For dioxygen difluoride, fluoride always has an oxidation state of -1. The sum of the oxidation states is 0. Since there are 2 fluorides, they contribute two negative oxidation numbers, and so they have to be balanced out by the oxygen. In this case, then, when you solve for the oxidation state of the oxygen, it must be a +1, which is not very typical. But what we see as a rule is that when you have multiple nonmetals in a compound, the most electronegative nonmetal gets its preferred oxidation state, and then the elements that are less electronegative, they must obtain whatever oxidation state makes sense, so that way the oxidation numbers balance out compared to the charge. And this is reiterated here in this last point. If you have shared electrons, if you have covalent bonds, then the more electronegative element gets the negative charge, and the other elements are going to have a positive oxidation number. So let's practice this. What's the oxidation number of phosphorus in Na2HPO4? So for disodium hydrogen phosphate, we see that we know that sodium must have an oxidation number of +1. It's a group 1 metal, and so it always has an oxidation number of +1 when it's in a compound. Hydrogen, generally speaking, will have a +1 oxidation number. Oxygen will, generally speaking, have a -2 oxidation number. And since oxygen is the more electronegative element, it gets its preferred oxidation number compared to phosphorus. Now, phosphorus is the one that we are not sure about. What we know is that the sum of the oxidation numbers must add up to be 0 because the charge on the molecule is 0. So we have 2 sodiums, each contribute an oxidation number of +1, 1 hydrogen, and 4 oxygens. If we then count in the oxidation number for phosphorus, that should add up to be 0. So when we simplify and rearrange, we see that the oxidation number of phosphorus must be 5. All right, here's a problem that I would like for you to try. As I've just mentioned already, we can identify redox reactions when there's a change in oxidation state. So for each of these 3 reactions, you need to identify the oxidation numbers or oxidation states of each element and identify if they are changing. So do that and then answer the question, which of the above reactions are redox reactions? Pause the video and try this on your own. Welcome back. So we need to identify the oxidation numbers of each element in each reactant and product. So any elemental substance has an oxidation number of 0. Aluminum, when it's on its own, is an element, so its oxidation state is 0. Fluoride typically has an oxidation number of -1. It would only be different if it's bound to a substance more electronegative than itself. Therefore, the copper must have an oxidation number of +2 because there were 2 chlorines, each -1. On the right side, we have chlorine with, again, an oxidation number of -1, which means that aluminum must have an oxidation number of +3. And copper, because it's elemental, has an oxidation number of 0. This is a redox reaction because the oxidation states of aluminum and copper are changing. Aluminum, we see, goes from 0 to +3. Therefore, it lost 3 electrons. It was oxidized. Copper went from +2 to 0. Therefore, it gained 2 electrons. It was reduced. Beneath it, we have aluminum, again at 0. Any monoatomic ion has an oxidation number equal to its charge. So for hydrogen, it's 1. Aluminum, it's +3 is indicated. And any element has an oxidation number of 0. So notice, even though hydrogen is diatomic, its oxidation number is still 0. So this one is also a redox reaction. We see that hydrogen and aluminum are both changing oxidation states. In the final reaction, we have 2 elements, hydrogen and oxygen, so therefore they're both 0. And hydrogen would have a +1 oxidation number, and oxygen would have a -2 oxidation number. So all 3 of these are redox reactions. Now, something to notice here, a shortcut, if you will. When you look at a substance that is elemental, so we have aluminum in the first reaction, and copper in the first reaction. If they're changing from an elemental form to a non-elemental form, meaning aluminum went from aluminum metal to aluminum in an ion compound, it has to change oxidation state. So once you do this enough and you recognize that, then you would actually be able to tell that all three of these are redox reactions without even determining the oxidation states. And that's because you are taking substances that are initially elemental and forming compounds, or vice versa. The last thing to talk about is the activity series. The activity series helps us to understand what the driving force is for redox reactions. For a redox reaction to occur, the energy of the products must be lower than the energy of the reactants. And so we can rank metals based on their stability, their redox potential. Within the activity series, elements up at the top of the series are highly reactive, whereas elements at the bottom of the series are very inert. And the activity series actually helps us to explain why certain metals are precious metals. So silver and platinum or gold are very expensive because they tend to not be non-reactive. They stay in their elemental form, in their pure form, whereas other substances like aluminum and magnesium and calcium are highly reactive, and so you can't find these substances in their pure elemental form very often. So that's it for this video. Thanks for watching. Have a great day.